Now we can see that the Markov chain can be used to sampling from a target distribution, even though we don't know the target distribution exactly. So in fact, the method, official method, is to design this Markov chain to sampling from a distribution is called Metropolis-Hastings method. So one can get a uniformly distributed point on the floor by walking around random for a long time. But if we want a different density, like we want to sampling, our target distribution is not uniform, right? Our target distribution is any arbitrary PDF, right, or PMF. Then we can bias our moves towards the region of a higher density, and by sometimes rejecting moves if they would lead us to a state of lower density than the current state. Okay, this is the main idea of this Metropolis-Hastings. Okay, so let's see how details we can design this Markov chain to sample any density we want. Suppose we want to simulate a representative random sample from a distribution pi on a set S. Right, so this pi is our target distribution and S is our sampling space. By the ergodic theorem, we can do this by running a Markov chain on S for a sufficiently long time. All we need is to set up a Markov chain that is irreducible and pi as its stationary distribution. Right, that's exactly what we did before. Now, how to do this? Use this Metropolis-Hastings method. This method can actually give you exactly what you want. All you need to do is just follow the steps. Later, we will prove why this method actually works. Now, first let's look at an easier version. We call it a Metropolis method. Suppose we want to have a Markov chain on the real line that has a density f as its stationary distribution. Okay, for example, let's plot a figure. So this is a real line, and let's say this is x, and this is x, random variable, and the vertical line is our target density fx. Okay, so let's see, the density is something like this. The arbitrary density. Okay, use the Metropolis method. Okay. Now what we want is that to get a sample from this distribution fx PDF, right? So let's suppose we're going to do this by running a Markov chain, right? So that our current state xt is at some point x. Let's see. Here is our xt equals to a number x at this location. Okay, so this point is fx, right? The current state is xt. We want to decide where to move next, so we can design a Markov chain, right? Your future only depends on the current state. This is done in the two stages, using this Metropolis method. Stage 1, choose a candidate state y from a particular density centered around x. Okay, for example, we could take a y randomly from the uniform density from x minus 1 to x plus 1. Okay, so x minus 1 to x plus 1, I think it's, just say, it's this region. Okay, this is x minus 1, this is x plus 1, and currently you are at X here, right? The Y is called a candidate state. It's uniformly taken around in this region. So let's, for example, we take a Y is here. Y is here. Okay, that's randomly sample from the uniform distribution. So this red color is Y. Okay, and here is Fy, right? Okay, right, that's stage 1. Stage 2, now we take a probabilistic decision about whether to accept the candidate. If we accept, that means xt plus 1, the next step will be equals to y. If we reject, that means xt plus 1 equals to where you are, that's the original value x. Right? So how are we going to decide this accept or reject? If this value of y, fy bigger or equal to fx, then we definitely going to accept this candidate y, and the next step xt plus 1 is directly going to y. So we move on as a Markov chain. Well, in our case, it's not bigger, right? Because this is x, this is y, this is fy is smaller, like fy smaller than fx. Then we're going to accept the candidate with a probability. That's fy divided by fx. Right? This ratio is always bigger than 0, smaller than 1. Right? So that means this. My next step, xt plus 1, will equals to y with the probability equals to this ratio. Or it can also equals to x with the original value with the probability 1 minus this ratio. Okay, so this is a random, you can see this is a probabilistic decision. Okay, then if you do this long time, run this Markov chain long time, now we can prove later that this Markov chain has the stationary distribution equals to f. Okay, so the Metropolis Markov chain consists of a long sequence of a repetition of this step. This stage 1, stage 2. Okay, so this is exactly how we can use Markov chains to sampling from any arbitrary distribution f, not necessary to be uniform.